first. Hi, everybody. Welcome to the first zk session today. We're going to have two talks. The first talk is going to be given by Chaya here. It's going to be about transparent constant size zkSNARKs. The construction's name is due. And this is John Ward. Lots of people are Zarun, Satya Lokhan, Tushar Mokuri, Sriram Sridhar. Shall we give the talk?
Thank you. Okay, so I'll talk about transparent constant size zkSNARKs today. Am I audible now? Okay, so I'll talk about constant size transparent zkSNARKs, and this is joint work with students Arasu, Tushar, and Sriram, and Satya, who is at MSR Research. Yeah, it was.
Right now?
Sorry. Okay, because this is the first zero knowledge session, I'm going to begin with succinct arguments. So let us look at argument systems where the prover would like to convince the verifier about the truth of some statement. So here there is a public function f, there is a public claimed output y, and the prover claims that f of w equal to y, claims knowledge of w such that f of w is equal to y. So they interact in a certain number of rounds, and then the verifier decides to accept or reject the proof. In addition to the standard properties of completeness and soundness, in a succinct argument, we also want the succinctness property, which can either be proof succinctness or verifier succinctness. In proof succinctness, we ask that the communication be logarithmic in the size of the statement and witness. And we also ask for verifier succinctness. We want that the verifier's computation is logarithmic. There is an exponential gap between computing the function f and verifying this proof. And a succinct argument system can either be proof succinct and verifier succinct, or just proof succinct. A zkSNARK is where additionally we have an initial setup in the beginning, and given the access to the setup, both the prover and the verifier have access to the setup. The proof is non-interactive, so the prover just sends a proof. It's a one-shot message sent to the verifier. We have succinctness, it's non-interactive, it is an argument of knowledge. And if we also ask for the zero knowledge property, it is a zkSNARK. For the purposes of this talk, we will be concerned with what kind of setup we have, in particular whether it is trusted or not. If there are secret random coins as part of the setup, we're going to call it a trusted setup. For the sake of concreteness, we can think of popular zkSNARKs that are based on KZG polynomial commitment scheme, or zkSNARKs like GROT16, where the CRS basically looks like this. It has powers of some secret s put in the exponent. And this s is actually a secret, which if revealed to the prover, it breaks soundness. So this is a trusted setup zkSNARK. I'm going to call SNARKs that have a setup that need not be trusted transparent zkSNARKs. And I'm going to show how to construct one such transparent zkSNARK that have constant size proofs. And towards building this, we are going to construct tools like inner product commitment schemes and polynomial commitment schemes. So here is our result in the context of state of the art. The construction of the polynomial commitment scheme I'll show you is going to yield SNARKs based on standard blueprints. And to put the resulting SNARKs in the context of the kind of constructions we already know, we know a transparent construction called DART from Eurocrypt 2020 that has logarithmic size proofs, logarithmic verifier. And unfortunately, there was a gap in the security proof of DART, which was pointed out by Block et al. In Crypto 21. They don't fix the gap, but instead propose a different polynomial commitment scheme that has polylog proof size and polylog verifier. In this work, we construct a transparent system we call DUE that has constant size proofs and logarithmic verifier, and it's in the GGM. In addition, we show how to recover the results of dark. In particular, we recover log proof size and log verification under the same assumptions as dark, which is adaptive root and strong RSA in groups of unknown order. Okay, so for most part of the talk, I'll focus on inner product commitment schemes and polynomial commitment schemes, and then dwell just a little bit on how to use these in order to compile information theoretic proof systems into cryptographic arguments. So let's begin with what a polynomial commitment scheme is. So here we have a prover who has a certain polynomial over some field of degree at most d. And the goal is for the prover to commit to this polynomial in a way such that later the verifier can ask the prover to open this committed polynomial at some evaluation point z. So they can then interact, and we want a small proof that attests to the correctness of this opening, that f of z is indeed y, and that this committed polynomial had degree at most d. So syntactically, we're going to have a setup algorithm that outputs some public parameters. We have a commit algorithm that takes the polynomial that the prover wants to commit to, outputs a commitment, and some opening hint that I'm going to call C tilde, which in the honest case is simply going to be the polynomial, but later in our constructions, we'll see how to exploit this opening hint. And an open algorithm that takes the polynomial, the commitment, the opening hint, and either accepts or rejects the opening. And then additionally, in addition to these three algorithms, we need an evaluation protocol, which is going to be an interactive protocol between the prover and the verifier for the following relation. Basically, the prover is claiming knowledge of a polynomial f such that f of z is indeed y, and it is consistent with the commitment that was originally sent. Right? So the verifier has the commitment, the point of evaluation z, the claimed evaluation y, the degree of the polynomial, the bound on the degree of the polynomial, and the public parameters. So they interact, and the verifier decides to accept or reject the proof. So the evaluation protocol is a protocol for this relation, and we want knowledge soundness for this. The efficiency properties we want is succinctness again. We want the commitment to be, the size of the commitment should not grow with the degree of the polynomial. It should be independent of d. And the communication complexity of the evaluation protocol, the proof size, should also be independent of the degree d of the polynomial that was committed to. And all our SNARKs are going to sort of inherit the succinctness property from the succinctness of this polynomial commitment scheme. So we want commitment binding, as usual with the commitment scheme. And in addition to commitment binding, we want evaluation binding, which roughly says that the prover should not be able to open the same evaluation point C to two different values of the same commitment C, which is also the same as asking for soundness of the evaluation protocol for this relation. A slightly stronger property is asking for extractability or knowledge soundness, which says that if the prover succeeds in convincing the verifier, then we actually want to extract a polynomial of the prescribed degree that is consistent with the opening and consistent with the commitment. Okay, and the transparency property is also going to be inherited from our polynomial commitment scheme. So we want our polynomial commitment scheme to be transparent, which means that the setup should only use public coins. So there are no secret coins in the setup procedure. So the roadmap is roughly going to be as follows. We're going to start with an inner product commitment scheme, and we will see that it sort of immediately gives us a polynomial commitment scheme as well. And a lot of the difficulty is in going from this immediate polynomial commitment scheme that has succinct proofs, but a non-succinct verifier, and going to a polynomial commitment scheme that has succinctness in both verification and the proof size. Okay, so what is an inner product commitment scheme? So here we have a vector C, where each entry in this vector is from some field ZP, and we are going to view this as integer entries from 0 to p minus 1. And we have a setup, and the commit algorithm takes this vector, outputs a commitment and an opening hint. There is the open algorithm that is as before. And here we have an evaluation interactive protocol that is to evaluate the inner product between certain query vectors from the verifier and the committed vector. Right, so the verifier can perform queries. She can ask inner products with the committed vector with Q. And the prover responds with the answer Y together with a short proof that attests to the correctness of that Y is indeed in a product of C and Q. So this is an inner product commitment, and if it is a succinct inner product commitment scheme, this evaluation protocol has the succinctness properties that we talked about before. Okay, so at the heart of all our constructions is an encoding method that takes vectors and gives us integers. And then we'll see how this encoding method gives us a commitment scheme. So we have this vector C of length L, and we're going to view them as integers in 0 to p minus 1. And now let us consider the vector consisting of powers of alpha, where alpha is carefully chosen such that all the entries in the vector are much less than this value alpha. Okay. And now we encode the vector by taking the inner product of this vector with this powers of alpha vector. This is our encoding. This gives us an integer. This takes us from a vector to an integer, and this is going to be our encoding. So how large should alpha be? This bound on alpha depends on our different commitment schemes, with different properties. In the proof, we derive some lower bounds on what alpha should be, and the max of all these lower bounds is going to be our alpha. But for now, let's just think that this is large enough for certain purposes that I'll tell you soon. And given that alpha is large enough, this is a good encoding scheme. Okay, so now we have an encoding. We took a vector, we went to an integer. So what do we do with it? I wanted to commit to a vector before. First, I take this encoding that I have. And now my setup is simply going to give me the description of a group of unknown order. So we heard about this from Damiano in the previous talk, where groups of unknown order have a transparent setup. So given this setup where I have a random group element from such a group, my commitment is simply putting this integer encoding of the vector in the exponent. So this is the commitment scheme. So why is this helpful? So we want an inner product commitment scheme. Ultimately, I want to be able to compute inner products with query vectors and the committed vector. So let's see why this is helpful. Let us consider, so this is my committed vector, and let us now consider a query vector. This is the inner product that we're interested in. And now I'm going to look at the reverse index of this vector. I'm going to take the reverse of this vector and apply the same encoding that we saw under the same encoding parameter alpha. Right? I'm going to encode the reverse of this vector Q. And these encodings are integers, right? I'm just writing them in sort of base alpha here. And let us look at the integer product of these. So if we consider this integer product, again, I'm writing this in base alpha. We see that the inner product that we are interested in sort of pops out as the coefficient of alpha to the L minus 1. Right? This is the inner product of interest. And again, all of this works when alpha is large enough and there are no problems. So now, how do we construct an inner product commitment scheme from this integer product? We want to convince the verifier about the correctness of this inner product. Right? So we can write this integer product. So what I have on the left is just the product of the two encodings, and I'm expanding them out on the right-hand side. If we look at this, the product on the right-hand side can be written as a sum of three sums. The middle thing is the one that we are interested in. That's the coefficient of alpha to the L minus 1, which is the inner product I want. And the rest I'm going to just call L and H, which are basically terms that have coefficients of alpha to the less than L minus 1 and greater than L minus 1 respectively. So now L and H are simply polynomials in alpha of degree less than L minus 1 and greater than L minus 1. And a first idea would be for the prover to simply send these two terms, L and H, so that the verifier can check this equation locally. Right? So I want to check this equation. And given the claimed inner product of C and Q, what does the verifier have? The verifier has the commitment, which is basically G raised to this encoding. So if I can raise G to both sides of this equation here, this is what I'm going to get, right? The left-hand side is G to the integer product of the two encodings. And G to the encoding of C was basically my commitment to the vector C. So this is simply C to the encoding of the reverse of Q. Does that satisfy this equation? And Y is basically the claimed inner product here. So the prover sends Y, and imagine for now that the prover also sends G to the L, G to the H, and we simply want the verifier to check whether this holds. So this encoding technique is sort of reminiscent of techniques used in prior works as well. But however, I mean, even KZG is sort of reminiscent of this, but note that alpha is not a secret. And we need new techniques to sort of prove that this works. So let us see what is our first protocol idea and what hurdles we face in proving it.
So that doesn't work, right?
That doesn't work.
Okay.
Yeah. Okay. So here is a naive idea. The prover sends the commitment, which is the encoding in the exponent. The verifier asks a query vector. The prover sends Y. And in addition, this is what I called sort of L and H, gamma and lambda are exponents of the correct terms put in the exponent again. This is what the verifier checks. This is just the equation from the previous slide. So how do we know that the prover computed these things correctly, right? L and H. So what I'm calling sigma here is basically the encoding of the reverse of the Q vector. And this is the equation that we wanted the verifier to check if the prover sent this gamma and delta correctly. But of course, the prover need not do this. So we are going to need proofs of knowledge of exponent. And here our starting point in order to achieve succinct proofs of knowledge of exponent is Veselowski's proof of exponentiation. So I'm going to give a very high level overview of Veselowski's proof and then show how to build the kind of proofs of knowledge of exponent that we are going to need in our construction. Okay, so as usual, we have a group of unknown order, and both the prover and the verifier have both Y and U, and the claim is that Y is U to the X. So here there is no zero knowledge for now. And what we want is that the verifier's work should be much less than computing U to the X on its own, right? Because X can be an integer that is much larger than the order of the group. So the protocol works as follows. The verifier is going to sample a random prime, and the prover computes the quotient and the residue, and now sends U to the Q. And the verifier can simply check that this was done correctly by checking that Q to the L, U to the R is Y. And note here that the verifier has to compute X mod L, but this is sort of still cheaper than computing U to the X, because computing U to the X is group operations, whereas this is free arithmetic. So now what we want is a proof of knowledge of exponent, where unlike in the previous slide, the verifier cannot compute X mod L because the verifier does not know X, right, the exponent. So here X is secret, Y and U are public, and the claim is knowledge of X such that Y is U to the X. So here the prover sends a first message that is basically the same exponent X with respect to a G that is part of the CRS. And again, the verifier samples a random prime. and the prover computes the quotient and the residue as before, but now this quotient is encoded with respect to both U and G that is part of the CRS. So we can think of this as sort of two POVs running in parallel, one with respect to the statement U and one with respect to a G that is part of the CRS. The prover sends Q, Q prime and R, and now the verifier need not compute the residue on its own, and it cannot because it does not know X, but it can check that the R that it received is in the correct range, and QL plus R sort of holds in the exponent. Okay. So now if we go back to so this proof of knowledge of exponent protocol, what properties does it satisfy? We know that this satisfies knowledge soundness in the GGM. So we can construct an extractor such that if the verifier accepts, the prover actually knows this exponent and the extractor gives us this exponent. So going back to our first protocol idea, so we had this equation to check the correctness of inner product, and now we additionally want a proof of knowledge of exponent from the prover for all the group elements that it gives us, the commitment and the two terms lambda and gamma. So note here that this still does not work because we kind of need to check that what is in the exponent are positive integers. So we need to check for positivity. So here we are going to construct a proof of knowledge of positive exponent, which is basically extending the protocol that we saw for proof of knowledge of exponent by using Lagrange's four-square theorem to decompose a natural number as a sum of four squares, and running a POKE protocol for each of these terms in the decomposition, and then checking that the decomposition was done correctly. So this is again running two POKs in parallel, one with U and one with G to the X, and checking that they're actually squares and that they decompose correctly, which gives us positivity. So ignoring a bunch of details, this is what our protocol is going to look like. It is mostly going to check that things are positive and they recombine correctly. And the extraction is simply going to come from the extractor for the POKE itself. And a lot of the work is going to go in arguing that we extracted the correct thing. So what guarantees do we get from this protocol? So given a commitment C and many accepting POKP protocols, one for all the group elements the prover sent, in particular for the commitment C, we can extract the exponent A, which we can write out in base alpha and sort of pull out the coefficients that we are interested in. So at best, this can give us knowledge of committed vector, but what about consistency with the claimed inner product? So we run into what we call the overflow problem when we try to show soundness. And the problem is the following. So recall that the inner product idea was to simply consider the integer product of the encodings and pull out the middle coefficient in the alpha base representation. And again, this works only when alpha is sufficiently large. But of course, a cheating prover could use large values of coefficient C. They need not come from 0 to p minus 1. And when this happens, the term that we pull out as the one corresponding to alpha to the L minus 1 is not quite the inner product because there is a lot of overflow from terms in the left. So extracting by base alpha representation does not give us the answer that we expect. So this is not really in a product of C and Q. So what do we do? So the idea to overcome this problem is to first double the length of the vector to 2L. And now we're going to place the vector that we want to commit to in even positions. And I'm going to ask the prover to put zeros in all the odd positions. So these are what we're going to call zero insertions. So let me call the vector that is being committed to C, and the zero vector I'm going to call D. So this is what we expect the honest prover to do. So we double the length of the vector and we ask that the prover commit by putting all the coefficients in the even positions of alpha and zero in the odd positions. So why does this help? So we can try to test for correct zero insertions. So how do we do this? We can devise a test protocol where we check that all the coefficients in the odd entries are zero by simply asking for an inner product with a random vector. So I'm going to place the random vector in the odd position, so they line up with D. And in all the positions lined up with C, there is zero. And if this inner product is non-zero, so this inner product is going to be non-zero, then D is non-zero with high probability by Schwartz. So this is going to be like a sub-protocol in our evaluation protocol where we first check that there are correct zero insertions. But this argument again is true only when C comes from the correct binding space, when C's are from 0 to p minus 1. So what happens when the prover, say, does the right thing by putting zeros in D positions but uses large values in the C positions? So here, the middle term that we expect to vanish in order to invoke Schwartz-Zippel is not quite the inner product of D and Q, but is corrupted by an error term that overflows from the C vector. Nevertheless, we are able to argue that if this middle term vanishes, we get some conditions on D and C that allows us to argue that C must be bounded. And we can obtain what we call a structure theorem on the D vector that later allows us to conclude soundness. So at a high level, our evaluation protocol is going to run in two phases. One, what we call the test protocol, that basically does what I described. If test passes, this is basically going to check for correct zero insertions and that C is bounded. So if test passes, we obtain a structure theorem that at a high level tells us that the coordinates of D can be rationals, but they have small denominators. We get a bound on the denominators of D. And if the test protocol succeeds, we move on to what we call the inner product subprotocol. And here the verifier can ask for a desired inner product with a desired query vector. And if this passes, we can extract a vector C tilde. And here we don't have the guarantee that we'll extract an integer vector. So C tilde is the opening hint that we saw earlier. So this can be fractional, but we have the guarantee that they have invertible denominators modulo P. And C tilde mod P is the unique vector, which is consistent with the commitment and the inner product. Okay, so just to sort of put things together, this is our inner product commitment scheme. Setup generates the description of a group together with an element G. Commit simply computes the encoding of the vector C with respect to alpha square. This is after the zero insertions. And the opening hint C tilde is simply the vector C. So open here checks for three different things. One, that C tilde is the correct, after I put the encoding of C tilde in the exponent, I get the correct commitment, and that C tilde is C mod P. Then there is this additional condition about the coefficients of C tilde itself, which roughly says that we are sort of expanding our binding space. So C tilde has this form, they're not integers, they're rationals, but we have a bunch of guarantees. The crucial one being that the denominators are invertible, and that is how we get our C. Okay. And the evaluation protocol has two subprotocols, test and IPP, and we do the IPP only if test passes. So if test passes, we get certain guarantees about the vector D. Then when we go to IPP, we extract from the POKPE extractor, and then using the structure theorem, we can argue that this is the correct unique vector. Okay, so we show commitment binding under the order assumption. And for extraction, we extract the exponent like we saw earlier using the POKPE extractor, write it out in base alpha, pull out the coefficients. And given that the test protocol passes, we obtain certain conditions on the D vector. And using these conditions, we show a global structure theorem that tells us what the rationals A by B look like. And given the structure, we can argue soundness of the IPP subprotocol that gives us knowledge soundness of the inner product. Okay, so why is this transparent? Because the setup is simply outputting a description of the group and a random group element. And these are class groups, so there are no secret points involved. Why is it succinct? Because the commitment is simply one group element. And the evaluation protocol is succinct. It has a few group elements from the POKP protocols. We can also batch them together. And about the verifier itself, we can also make the test protocol succinct by generating the test query vector from a PRG instead of sending the entire vector. The verifier can also be made efficient by offloading expensive exponentiation via proof of exponentiation. Okay, so this was our inner product commitment scheme. Now this immediately gives us a polynomial commitment scheme as well. So let us see how to specialize an IPC to a PCS. So I have a polynomial of degree at most d. And in order to commit to this polynomial, I simply look at the vector of coefficients of this polynomial and use the commitment scheme that we just saw. I use the IPC commitment scheme. And in order to evaluate this polynomial at a certain point z, we can simply take inner products with a very structured query vector that is powers of z, where z is the desired point of evaluation. So this already gives us a polynomial commitment scheme. And before I get to the succinctness properties of the polynomial commitment scheme, now that we have a PCS, how do we obtain a SNARK that has a transparent setup using this PCS? These are not new ideas. These are standard techniques, but I still want to show how to get there. Okay, so the modular approach that was advocated by Isha et al. Like in 2007 and has been adopted in most of the recent works is to start with the relation that we want to prove things about and get an intermediate representation that can either be like a quadratic arithmetic program or a rank one constraint system or an arithmetic circuit, and then construct an information theoretic proof system for this representation. And this information theoretic proof system can be PCPs, linear PCPs, IOP, polynomial IOP, etc. And then we apply a cryptographic compiler that converts this information theoretic proof system into a cryptographic argument. Now that we have a polynomial commitment scheme, our cryptographic compiler is going to be a polynomial commitment scheme, and we can compile objects like PIOPs that are polynomial IOPs and AHPs that are algebraic holographic proofs. So at a very high level, how does this work? How do we go from PCS to SNARK? So in a polynomial IOP, the prover is going to send certain polynomial oracles to the verifier, and the verifier can interact with this oracle by asking for evaluation of the polynomial at certain points. The prover can also interact with the verifier after sending the oracle. It can also send more oracles later. And at the end of this, the verifier can accept or reject this polynomial IOP proof. And now in the compiled argument, the argument prover is going to use a polynomial commitment scheme in order to realize these oracles. And the interaction of the IOP verifier with the oracle is replaced with the evaluation protocol that is given by the polynomial commitment scheme. And the argument prover reveals the evaluation at the queried points together with a short proof that this was indeed correct. Okay, so to go from a polynomial commitment scheme to a SNARK, we start with an information theoretic proof system, use our polynomial commitment scheme to compile it into a succinct cryptographic argument. And if the polynomial commitment scheme is public coin, then we can apply Fiat-Shamir and make this non-interactive and obtain a SNARK. The final SNARK inherits the properties like proof size and verifier complexity from the polynomial commitment scheme. So the SNARK that we are going to get from the polynomial commitment scheme that we saw will have succinct proof size and all other assumptions inherited from the PCS. Transparency, and that is why we get a transparent SNARK. Okay, so this was our specialization of an inner product commitment scheme to a polynomial commitment scheme. This was easy. We just asked for inner product with a structured query vector. But now let us look at verifier succinctness. Right? Do we actually have succinct verification? So if we go back to our evaluation protocol, we had these test and IPP subprotocols. And the IPP protocol for a polynomial commitment scheme has a structured query vector. However, the test protocol requires a random query vector, and all the guarantees that we get, including the structure theorem about the rationals, are only when this is a random query vector, right? And this needs to check for correct zero insertions, obtain bounds on C, obtain the structure about D, and so on. So this is as long as the committed vector, and this makes the verifier linear. So what do we do about this? So this was our sort of stripped down naive protocol idea, and this is what the verifier is doing. Sigma is the encoding of the reversal of Q, where Q is the random query vector in the test subprotocol. And computing the encoding. Computing sigma, computing the encoding of the reversal of Q is what makes the verifier linear. This is the bottleneck for succinct verification. So what can we do about this? So note that earlier I said we can offload this exponentiation here, C to the sigma, to the prover using Veselowski's proof of exponentiation. However, in Veselowski's proof of exponentiation, the verifier has to compute x mod L, where x is the exponent in the proof, right? So in our setting, this is going to be, x is going to be sigma, and the verifier has to compute sigma mod L for some random prime L. And computing this this encoding for random Q is going to be linear time. So what do we do about this? The first idea is to not use a random query vector in our test protocol. Instead, use Kronecker products to sort of compress the amount of randomness that the verifier has to work with in test. So what do we do? Instead of choosing an L length random vector Q, I'm going to sample 2 root L random elements and just compute the query vector Q for the test protocol by taking products xi, yj for every I and j. Right? So this is what we're doing in the test protocol because that was the bottleneck for verifiers computation. And now, if we look at what the POE verifier would do, which is basically computing sigma mod Q prime for some random Q prime, which made the verifier linear, we can rewrite this encoding of reversal of Q, where Q is structured in this way as Kronecker products. We can rewrite this sigma mod Q prime as the product of 2 sums. And now, by carefully choosing alpha, the lower bounds of which is given from our proof, we can make computation of this sublinear. So if alpha is p to the root L, we can compute sigma mod Q prime in time that is sublinear, and everything can be in root L. So here this can be computed in root L time. Okay, so why do we stop at root L? We can extend this to beyond. So can I take log L vectors of length 2 each and do the same Kronecker product idea? So now my query vector Q is just going to be a Kronecker product of these log L length vectors. So instead of 1 vector of length L, I have log L vectors of length 2. So this works. I mean, it extends as an idea, but what breaks is soundness. So how did we extract earlier? All the structure guarantees that we got about the rationals, the C and D, was because of the randomness of Q. And now we don't have those guarantees anymore because Q is not random. In the log L case, we have an exponentially small randomness space, and we still have to argue correct extraction. This is not a random query, and therefore our soundness proof breaks. So proof of the structure theorem on D coordinates, it does not follow anymore. So what we need is, we're going to need multiple equations with structured randomness in order to conclude similar conditions on the D vector as before. And at a very high level, the way we do this is by invoking a combinatorial lemma, the two-dimensional version of which is the following. So we ask, given a binary n cross n matrix, what is the number of ones such that there is no rectangle? And for the 2D version, we know bounds for this question, which is like n to the 3/2. And using these bounds, we can get similar structure guarantees on the D vector. At a very high level, what is the connection between the lemma and our proof? We think of the query vectors as points in this space. So for every one that we have a test protocol that was successfully accepted by the verifier. Right. And if the prover succeeds with non-negligible probability, then we know that there must be enough ones. And once we have enough ones in the space, we can write out equations that we get from the verification equation. And they have structure simply because of the Kronecker products in the random variables of the product. And that allows us to conclude soundness. So this bound is known for the case when D is equal to 2, and this allows us to go only up to square root verification. In order to go up to log, we have to show a different lemma because the existing bounds do not suffice. So the existing box theorem for D larger than 2 gives us bounds like n to the D minus 2 to the minus D. For growing D, this is not sufficient for arguing good probability of extraction. So here we define general D structures. These are 3 structures here, which allows us to prove tight bounds on the number of points that do not contain a D structure. And the bound that we can show is something like D times n to the D minus 1. This is a vanishingly small space in the entire space, which is n to the D. So in our application, n is like p, which is where the random points come from, and d is like log p. And intuitively, each successful run of test by the prover corresponds to choosing a point in this discrete space n to the d. This will be the space of randomness. And these bounds allow us to recover the same structure theorem that we had in the linear case for the logarithmic case, giving us constraints on D, and our extraction proof will go through. Okay, so that was our polynomial commitment scheme that has succinct proof size and succinct verification. In the time that I have left, I want to say a little bit about the gap in the proof of security of dark and how we recover the dark results. So at a very high level, the dark polynomial commitment scheme is transparent, works in groups of unknown order, and sort of syntactically has the same commitment scheme that I showed before. But the evaluation proof is logarithmic because it's a split and fold recursive protocol where in each round, so the commitment is still putting an encoding of the vector in the exponent. And in order to prove evaluations that f of z is equal to y for some verifier chosen point z, the prover is going to break the polynomial up into the left half and the right half, sort of create instances that are half the original size. send evaluations of both these polynomials at z. The verifier checks that this was done correctly, and then the verifier sends the challenge beta around which the instances are folded, and then they recurse on the new instance c prime and y prime. So this is the evaluation protocol, and the extraction works by the extractor rewinding and creating a tree of many transcripts from which it can extract for different challenges beta. So the gap in the extraction proof is that the proof makes an implicit assumption that if C and A, where A divides C, both have small digits in base Q, then so does C by A. This is an implicit assumption they have in the proof where the extractor sort of recombines from the earlier level to get a witness at the next level. But this is not true, and a counterexample for this was shown in Block et al. In Crypto 21. And the reason this matters is that the extractor has to recombine outputs at every stage. It's rewinding the prover and extracting. And this fails because the prover could commit to rational polynomials such that the random linear combination in some round where the verifier chose the randomness gives an integer polynomial. So the original polynomials need not be integers. Unlike the commitment scheme I showed you, the dark scheme did not allow for rational openings, and that is why the extractor failed. I must say that this paper is recently fixed and revised on ePrint. The same protocol is shown to satisfy extraction, but with adjusted parameters. The way we recover dark is that our point of evaluation is alpha square instead of the point of evaluation q used by the original dark scheme. And by appropriately setting the bound on alpha, we can show that the same split and fold evaluation protocol with our commitment scheme and encoding scheme works, and the extractor can actually recover a witness that is within the binding space of our commitment scheme. The increased bound on alpha also means that our prover is quadratic, unlike the quasi-linear prover of dark. Okay, so I did not say much about zero knowledge, and I'm not going to say much about it either. We can make our commitments hiding by adding a large enough random degree d+1 coefficient, and we can make our evaluation protocols zero knowledge as well, using standard techniques that have been used in dark and even prior works. Before I stop, I just want to outline some future directions. So in transparent SNARKs, we get constant size proofs, but there are still 70 group elements. So concrete efficiency is still something that is that needs a lot of work. And can we build transparent SNARKs from other assumptions? Prover efficiency is also something that we did not focus on. Our prover is quasi-linear, but the constants, we haven't looked at the constants. Another question is, we build IPCs and PCS. Can we build functional commitments with constant sized openings for other functions, for specific useful algebraic functions, not necessarily for compiling into SNARKs, but for other applications like verifiable databases or computation on authenticated data and so on. That's all I have. I'm happy to take questions.
Okay, any questions? All right, a couple of quick questions. So, did you mention concretely what is roughly the ballpark proof size in terms of group elements and elements? How much is it going to be?
Like something between 60 and 70.
Okay.
So it depends on the underlying HP that we compile, because we can batch our evaluation proofs. And now it depends on how many polynomials we have to commit to. So if it's Marlin, it's like, depends on the number of polynomials. I think Blanc has like 11 polynomials, so it's 11 plus.
Right. And then a question, really quick, that you're going to hit me for maybe. So you achieve a constant size. I think there's lots of nice techniques and challenges here, but I'm curious about this. Would you respond to this? You achieve a constant size proof. But the proof, I mean, maybe you have ideas on how to compress it, but the concrete efficiency in practice is still, we're still far from that. How would you motivate this as a theoretical achievement in that direction. You know, like it's easy to even see how to push that in that concrete direction.
Yeah, no, I don't have a good answer. I think so. We did the very straightforward batching things that we could think of. You know, batch the PFA proofs, batch evaluation, multiple evaluations of the same polynomial, and so on. But I think a lot of other things are unexplored in terms of concrete efficiency that we could push for. But I also think that the kind of techniques that we show could be useful to push other log size proofs to constant size proofs.
Thank you. Let's thank the speaker.